Before the world burned, before air raid sirens fractured the silence of European nights, before aircraft became shadows of destruction instead of symbols of wonder, there was a machine that promised something extraordinary. In the late 1930s, aviation still carried the scent of adventure. Airports were not yet sprawling fortresses of steel and glass, they were modest fields of ambition. Terminals echoed with nervous excitement. Pilots walked across tarmacs without security details or ceremony. Flying was not routine, it was an event. Cabins rattled at altitude, windows vibrated against thin frames, engines spat smoke and oil into uncertain skies. A transcontinental flight required multiple stops. An ocean crossing felt like a gamble against weather, fuel, and mechanical endurance. Passengers dressed in suits and dresses not because it was comfortable, but because stepping onto an aircraft felt historic. There was elegance in the risk. Yet inside the design rooms of Douglas Aircraft Company, romance was not enough. Engineers leaned over drafting tables under harsh white lights, asking a dangerous question. What if flight could become inevitable? Not fragile, not experimental, inevitable. They did not want to refine the present, they wanted to replace it. The answer to that ambition emerged in aluminum and rivets, the Douglas DC-4E. Even the name felt technical, almost cold, but what it represented was anything but ordinary. This was not simply another airliner, it was scale redefined. 4 engines mounted along a wing so broad it seemed to stretch beyond proportion, a fuselage designed for space rather than survival. Electrical systems replacing older mechanical linkages wherever possible, redundancies built into its architecture like layers of silent insurance. And then there was the stance. Unlike the tail-dragging aircraft that dominated airfields, the DC-4E stood upright on tricycle landing gear, nose forward, confident, modern. It did not crouch like its predecessors. It faced forward. From a distance, it appeared imposing. Up close, it felt improbable. Mechanics walked beneath its wings and instinctively lowered their voices. Executives studied its silhouette against the hangar doors, imagining headlines, imagining routes that stretched across oceans without apology. The aircraft promised longer range than most commercial transports in existence. It promised smoother flight characteristics. It promised a cabin experience that suggested the sky could be crossed in dignity. But innovation carries weight, literal weight. Each new system added wiring. Each improvement required reinforcement. Each ambition demanded structure. And structure meant mass. When the prototype rolled out of the hangar for the first time, the moment felt rehearsed by history itself. Workers stopped mid-task. Tools froze in greasy hands. Even the wind seemed to hesitate. The sunlight reflected off polished aluminum, turning the aircraft into a mirror of possibility. Some saw profit. Some saw prestige. A few saw risk. The day of its first full-power engine run drew a quiet crowd. No banners, no speeches, just anticipation. The propellers began turning slowly, blades slicing through morning air. One engine ignited, then another, then another. Finally, all 4 roared in synchronized thunder. The ground vibrated. Loose gravel danced along the runway. Windows trembled in nearby buildings. Conversations vanished beneath mechanical force. Inside the cockpit, test pilots scanned instruments with disciplined calm. Oil pressure, temperature, RPM. Every needle mattered. This was no longer theory. This was consequence. Brakes released. The aircraft began to roll. Heavy at first, deliberate, almost reluctant, as if aware of the expectations placed upon it. Speed increased. Wind pressed against its broad wings. For a fleeting second, doubt hovered. Was it too heavy? Too ambitious? Too early? Then lift arrived. Subtle at first. The wheels separated from Earth, and the massive aircraft rose into California sky. Not gracefully, but undeniably. Below, observers tilted their heads upward. Some shielded their eyes against reflected sunlight. Others simply stared. The DC-4E climbed steadily over the coastline, its 4 engines carving a steady rhythm into the air. In that moment, it seemed obvious. This was the direction aviation would take. Larger aircraft, greater comfort, increased complexity harnessed into reliability. The future appeared visible, tangible, already airborne. But history rarely unfolds in straight lines, because beyond the applause of that first flight waited realities far less romantic than ambition. Balance sheets, fuel consumption charts, maintenance projections, and a world inching closer to war. The sky had accepted the giant. Now the world would decide its fate. From the outside, the DC-4E looked unstoppable. From the inside, it felt revolutionary. The cabin was wider than passengers expected. The aisle allowed movement without awkward turns of the shoulders. The seating layout suggested that long-distance travel could be endured with dignity, perhaps even comfort. Large windows invited sunlight instead of claustrophobia. The noise level, while still unmistakably mechanical, was more controlled than most transports of the era. This was not just transportation, it was a statement. Airlines initially watched with fascination. Executives imagined premium transcontinental routes, New York to Chicago, Chicago to Los Angeles, eventually, perhaps, even transoceanic flights without constant refueling stops. Prestige mattered, and this aircraft radiated it. Test flights reinforced optimism. Pilots reported stable handling in cruise. The Tricycle landing gear simplified ground operations and improved forward visibility during taxi. Takeoffs felt more controlled compared to older tail-dragging designs. In turbulence, the broad wings delivered reassuring stability. Technically, the airplane worked, but engineering success is not the same as economic survival. Every innovation carried hidden mass. The complex electrical systems required miles of wiring. Structural reinforcements added strength and weight. Redundant safety features, though forward-thinking, increased mechanical density. The aircraft was not just advanced, it was heavy. Fuel consumption numbers began to emerge from test data. They were not catastrophic, but they were uncomfortable. 4 large engines required significant fuel flow. The aircraft's weight demanded power, power demanded consumption, and consumption demanded revenue. Airline accountants began running projections that had nothing to do with aerodynamics. They studied maintenance intervals, spare part logistics, crew training costs, infrastructure upgrades required to handle a larger airframe. The answers were sobering. Operating costs exceeded expectations. Profit margins narrowed dangerously. Ticket prices would need to increase to justify regular service, and the flying public of the late 1930s was still limited. Air travel was growing, yes, but it was not yet a mass-market industry capable of absorbing such expense. Behind closed doors, meetings shifted in tone. Excitement softened into hesitation. Hesitation hardened into caution. The DC-4E was not failing in the air, it was failing in the ledger books. And timing could not have been worse. The global economy was still recovering from depression. Political instability in Europe was escalating. Military tensions were rising across continents. Airlines were cautious. Expansion plans became conservative. Risk tolerance shrank. In that environment, the world's most advanced airliner suddenly looked like a gamble. Orders that had once seemed promising slowed dramatically. Then they stopped. The prototype, once surrounded by engineers and photographers, began spending longer hours alone inside its hangar. Its polished aluminum skin reflected overhead lights instead of sunlight. Its engines, once symbols of ambition, sat silent for days at a time. To some, it was simply too much airplane, too complex, too expensive, too early. Yet the irony was unmistakable.
The very features that made the DC-4E extraordinary were the ones that made it unsustainable. It was not poorly designed, it was not unsafe, it was not incompetent. It was ahead of its ecosystem, a machine built for an aviation industry that did not yet exist, and that mismatch is often fatal. Inside Douglas Aircraft Company, engineers faced a quiet reckoning. They had proven what was technically possible, but possibility without adoption leads nowhere. The aircraft had demonstrated advanced systems integration years ahead of widespread implementation. It had proven the aerodynamic feasibility of larger transports. It had introduced configuration choices that would later become industry standards. But it could not convince airlines to risk their survival on its promise. And so the most advanced commercial airliner America had yet produced found itself in limbo. Too valuable to scrap, too expensive to operate, too ambitious to scale back easily. What happens to innovation when the market rejects it? Sometimes it disappears. Sometimes it waits. And sometimes it finds a buyer who sees not risk, but opportunity. Across the Pacific Ocean, observers were watching closely, not with caution of accountants, but with the urgency of strategists. Because in another nation, under another set of priorities, the equation looked very different. For them, profitability was not the primary concern. Range was, payload was, strategic reach was. The DC-4E had failed to conquer the commercial sky, but it had proven something undeniable. A four-engine giant could fly, and in a world inching towards total war, that proof mattered far more than ticket sales. The hangar doors would open again, not for passengers, but for history.
Failure is rarely the end of a story. Sometimes it is simply a change of ownership. As American Airlines distanced themselves from the DC-4E, the aircraft did not vanish into obscurity. Its test data circulated quietly through technical channels. Aviation magazines discussed its radical configuration. Military observers took notes. Foreign attachés listened carefully. Across the Pacific Ocean, in an empire expanding its strategic reach, interest began to solidify. Japan in the late 1930s faced a geographic reality that shaped its military thinking: distance. The Pacific was vast. Supply lines were long. Strategic bombing capability lagged behind other global powers. The Imperial Japanese Navy and Army both understood that future conflict would demand aircraft capable of flying farther than ever before. And here was proof that such size was possible. The Douglas DC-4E represented something invaluable: experience already paid for. Years of aerodynamic experimentation, structural solutions to high weight loads, systems integration in a four-engine configuration. Negotiations began discreetly. There were no dramatic public announcements, no press conferences declaring technological exchange, just paperwork moving quietly between corporate offices and international intermediaries. Eventually, a deal was reached. The prototype, America's boldest commercial airliner experiment, would be sold. It was a transaction that, at the time, seemed minor. After all, the aircraft had no confirmed airline future. It was an expensive prototype without a market. Selling it recovered cost and cleared hangar space. But history would view the moment differently. The aircraft was carefully disassembled, wings detached, engines removed, control surfaces cataloged, every structural component documented. The process resembled surgery, precise, deliberate. Crates were constructed to protect sensitive assemblies. Blueprints and technical documentation accompanied the shipment. The pieces were transported by ship across the Pacific, moving steadily westward. By the time the public fully understood what had occurred, the DC-4E was no longer on American soil. In Japan, engineers waited. When the crates were opened, the atmosphere reportedly carried a mix of excitement and pressure. This was not simply a foreign aircraft, it was a technological shortcut. Every rib inside the wing told a story about load distribution. Every cable routing choice revealed problem-solving decisions refined through trial and error. The fuselage structure demonstrated how to manage stress across a large pressurized body. But the Japanese engineers were not interested in passengers. They were interested in range. They were interested in payload. They were interested in war. The aircraft became a three-dimensional classroom. Measurements were measured meticulously. Reverse engineering began. The goal was not to reproduce an airliner. The goal was to build a heavy, long-range bomber capable of projecting power across the Pacific. From these efforts would emerge the Nakajima G5N. On drafting tables, the transformation began. The elegant passenger cabin concept was erased. Seating configurations disappeared. In their place, bomb bays were drawn into the belly of the aircraft. Reinforcements were added to carry military payloads. Defensive gun positions were integrated into the fuselage. What had once promised luxury would now carry destruction. Yet a crucial misunderstanding lingered beneath the enthusiasm. The DC-4E had been advanced, but it had also been heavy, complex, and difficult to operate economically. Its struggles were not random. They were symptoms of pushing engineering boundaries without fully mature industrial infrastructure. Copying the external geometry was possible. Copying the invisible refinement behind it was not. Still, the strategic logic felt compelling. If American engineers had proven that such a large aircraft could fly, then adapting that concept for military use seemed logical. Japanese planners envisioned long-range strike missions against distant bases. They imagined aircraft capable of reshaping the balance of power in the Pacific theater. A true heavy bomber, something that could rival Western designs, appeared within reach. On paper, the specifications were impressive. 4 engines, substantial bomb load, extended operational range. For a moment, it seemed as though the rejected American prototype had found a new destiny, one far more consequential than carrying passengers between cities. But engineering ambition and strategic ambition are not the same. As the first airframes began to take shape, subtle warnings emerged. Engine performance did not perfectly match projected requirements. Structural weight increased beyond initial calculations. Integration challenges multiplied. The DC-4E had been a complex machine built by a mature industrial ecosystem. Recreating that ecosystem was far more difficult than shipping crates. Yet momentum had already begun. Factories adjusted. Engineers worked late. Military officials anticipated results. The prototype that America deemed too expensive now stood at the foundation of a weapon program. And as tensions across the Pacific escalated towards open conflict, the urgency intensified. Because once war begins, there is no time left for experimentation. The sky demands results. And soon the G5N would be asked to prove that copying ambition was enough. History was about to test that assumption. On paper, the new bomber looked formidable. Large wings capable of carrying immense fuel reserves. A fuselage wide enough to house bomb bays and defensive positions. 4 engines promising the power required to cross vast stretches of ocean. The Nakajima G5N was envisioned as Japan's answer to the growing importance of long-range strategic aviation. Military planners imagined formations of these giants lifting off at dusk, climbing into darkening skies and disappearing over the Pacific horizon. They imagined distant bases suddenly within reach. They imagined power projected not just across seas, but across psychology. But blueprints are forgiving. Reality is not. The original Douglas DC-4E had already struggled under the burden of its own ambition. It had been heavy, complex, expensive to operate. Its systems were advanced, but they required an industrial base prepared to support that complexity. Japan's engineers now faced the same physics without the same foundation. The first problem was engines. The G5N required power plants capable of lifting a massive airframe loaded with fuel and bombs. but the available engines did not consistently deliver the output required to match projections. On test stands, numbers seemed acceptable. In the air, under stress, they revealed limitations. The second problem was weight. Military modifications added reinforcement. Bomb bays required structural adjustments. Defensive gun positions introduced further mass. Each solution to one requirement quietly created another problem elsewhere. Aircraft design is a delicate balance between lift, thrust, drag, and weight. Tip that balance too far in one direction, and performance collapses. As prototypes neared completion, engineers already sensed the tension between ambition and practicality, but the geopolitical climate allowed little room for hesitation. War was no longer theoretical, it was approaching with speed. When the first G5N rolled onto the runway for testing, the moment carried immense expectation. Ground crews stepped back. Test pilots climbed into unfamiliar cockpits. 4 engines ignited in staggered sequence, their vibrations pulsing through the heavy frame. From a distance, the aircraft looked imposing, almost majestic. Its size alone suggested capability. Its silhouette projected strength. But perception does not generate thrust. As throttles increased, the aircraft began its takeoff roll. Acceleration was slower than anticipated, longer, heavier. The runway seemed endlessly ahead. Inside the cockpit, eyes flicked between instruments, airspeed rising but not quickly, engine temperatures climbing, control inputs steady but firm. Finally, lift. The aircraft separated from the ground but without confidence. The climb rate was shallow. The nose angle required careful management. There was no sensation of excess power, no margin to spare. Once airborne, additional issues surfaced. Control response felt sluggish. Structural vibrations appeared at certain engine settings. Engine cooling remained a constant concern, especially during prolonged climbs. Each test flight produced new data. Each datasheet produced new complications. Engineers attempted modifications. Reinforcements were adjusted. Weight reductions were explored. Systems were rebalanced. But each correction required compromise. And compromise, in aviation, accumulates. The G5N was not catastrophically flawed. It simply never reached the standard required to justify its existence. Range fell short of the most ambitious projections. Payload had to be reduced to preserve performance margins. Reliability remained inconsistent. In a wartime environment where efficiency and dependability decide outcomes, almost adequate is rarely acceptable. Production numbers remained low. Only a limited number of airframes were completed. Some were reassigned to transport duties, others were quietly sidelined as more practical aircraft took priority. The dream of a Japanese 4-engine strategic bomber, born indirectly from an American commercial prototype, began to dissolve. But the deeper lesson was more profound than a single failed program. The DC-4E had represented a leap beyond its ecosystem. The G5N represented a leap without one. Aircraft are not just shapes. They are industrial expressions of experience, of manufacturing precision, supply chains, metallurgy knowledge, engine development cycles, and thousands of invisible refinements accumulated over time. Those refinements cannot be shipped in crates. They cannot be retro-engineered from rivet spacing alone. They must be earned. And in the skies of Japan, that truth became undeniable. The G5N could fly, but it could not dominate. It could carry weight, but it could not carry expectation. What began as an attempt to leap forward technologically had become a demonstration of the limits of imitation. But across the Pacific, in the very nation that had sold the original prototype, engineers were watching the evolution of large aircraft with a different mindset. They had seen the DC-4E struggle under complexity. They had watched their own creation become something else entirely, and they were learning. Because sometimes the greatest breakthroughs are not born from success, they are carved from failure. And the next chapter of this story would prove that understanding balance matters far more than pursuing scale alone.
The sky is impartial.
It does not care about ambition. It does not respect political urgency. It does not negotiate with expectation. It only responds to physics. By the time the Nakajima G5N entered extended flight testing, optimism had already begun to erode. Reports from early sorties revealed patterns too consistent to ignore. Takeoff runs remained dangerously long. Climb performance lagged behind operational requirements. Engine reliability continued to raise concern, particularly under full military load. Test pilots described the aircraft not as aggressive or powerful, but as strained. Controls required deliberate input. Maneuvering demanded anticipation. There was little sense of excess capability, no feeling of reserve power waiting to be unleashed. And in wartime aviation, reserve is survival. The bomber's projected range, once its most celebrated attribute, required careful recalculation. Under realistic payload conditions, the numbers narrowed. Bomb load had to be reduced to preserve acceptable flight characteristics. Every kilogram removed from bombs felt like a strategic compromise. Maintenance crews faced their own battle. Complex systems required attention. Engine servicing consumed time and resources. Spare parts logistics became an operational burden. The aircraft was not merely flying missions, it was demanding constant support between them. And support is expensive. Only a limited number of G5Ns were completed. Production never reached the scale originally envisioned. Some airframes were reassigned to transport roles, where payload mattered less than reliability. Others were gradually withdrawn from frontline relevance as alternative aircraft designs proved more practical. The dream of a long-range heavy bomber capable of reshaping Pacific warfare faded into technical memoranda and quiet reassignment orders. It was not a dramatic collapse. There was no single catastrophic failure that ended the program. Instead, there was something more definitive: accumulation. Accumulation of underperformance, accumulation of maintenance hours, accumulation of compromise. The sky had rendered its verdict slowly, methodically, without spectacle. Meanwhile, across the Pacific, the original creators of the concept were confronting their own realization. At Douglas Aircraft Company, engineers understood something essential. The failure of the DC-4E had not been random. Its complexity, its weight, its economic impracticality, these were warnings. Warnings that innovation must align with infrastructure. Warnings that engineering brilliance without operational balance becomes liability. The DC-4E had been too advanced for its commercial ecosystem. The G5N had been too ambitious for its industrial ecosystem. Different nations, different purposes, same gravity. In both cases, scale had outrun sustainability. And yet, neither program was meaningless, because buried within every failed takeoff roll, every overheating engine, every disappointing climb rate was data. Lessons written in vibration patterns and maintenance logs, insights that could not be learned from success alone. The G5N proved that copying form does not guarantee function. It proved that strategic desperation cannot substitute for engineering maturity. It proved that ambition without equilibrium collapses under its own mass. By the middle years of the war, the aircraft that had once symbolized promise no longer occupied center stage. New designs, better aligned with practical demands, took priority. The G5N receded into the background of history, not erased, but diminished. And yet, its story mattered more than its production numbers suggested, because sometimes an aircraft changes history not by dominating the sky, but by revealing its limits. The DC-4E had been a bold question. The G5N had been an attempted answer. Both had struggled. Both had fallen short of their intended destiny. But far from the noise of battle, in quiet design rooms filled with blueprints and calculation tables, another philosophy was beginning to take shape. One that rejected excess. One that respected balance. One that understood that the true measure of an aircraft is not how impressive it looks on paper, but how reliably it performs under pressure. The age of giants built purely for ambition was ending. The age of disciplined practicality was beginning. And from the ashes of two overreaching machines, a different kind of aircraft was about to emerge, one that would not seek to impress the world, only to serve it. The final lesson was coming, and this time, the sky would approve. Back in the United States, the story of the DC-4E was far from over. Its failure, or more accurately, its lessons, became the foundation for something profoundly different. Douglas engineers studied every logbook, every maintenance report, every flight test. They examined each failure not as shameful mistake, but as a guide. Where the DC-4E had been too complex, they sought simplicity. Where it had been heavy, they sought weight reduction. Where ambition had outpaced practicality, they sought reliability. The philosophy was clear. Perfection in concept is worthless if the aircraft cannot be produced, maintained, and flown consistently. Brilliance in isolation means nothing when lives depend on it, when war demands endurance, when logistics defines success. And from that crucible of lessons came the Douglas C-54 Skymaster. The C-54 was not glamorous. It did not turn heads with sweeping wings or futuristic landing gear. It was not a conversation starter for airline executives or a marvel to photograph in sunlight. But it worked. Every day, in every condition, over oceans, over mountains, in deserts, in storms. Its engines were dependable, its systems manageable, its construction logical, standardized, and repeatable. Thousands were produced. The C-54 carried soldiers to distant battlefields, transported medical supplies to the front lines, delivered food to populations in crisis, and evacuated the wounded to safety. It connected continents in ways no previous aircraft could achieve reliably. Its quiet service underpinned the Allied logistical efforts in the Second World War. While the G5N had struggled with ambition, the C-54 thrived on practicality. It embodied the lesson the DC-4E had silently taught. An aircraft must harmonize ambition with reality, power with control, innovation with sustainability. The DC-4E had dreamed of revolution. The G5N had sought to impose that dream militarily. Both had failed in execution. But their failures were not in vain. They carved the path for an aircraft that could operate at scale, day after day, mission after mission, without spectacle, but with decisive impact. Aviation does not progress in leaps alone. It progresses in iterations, in careful observation, in the disciplined study of error. For every prototype that collapses under its own weight, every engine that overheats, every flight test that barely reaches its intended range, knowledge is gained. Knowledge that becomes invisible wings supporting the next design. Knowledge that keeps people alive. Knowledge that wins wars. So when we look at the skies today, or when historians note the aircraft that carried victory across oceans and battlefields, it is worth remembering the forgotten giants, the machines that could not survive the ledger, the airframes that could not dominate the Pacific, the experiments that faltered because the world was not yet ready for them. Because sometimes the aircraft that failed spectacularly is the one that teaches the lessons others need to fly. The DC-4E may never have carried passengers in comfort. The G5N may never have delivered bombs effectively, but their stories were not wasted. They wrote a blueprint in experience, in trial, in error. That blueprint gave birth to the C-54, which quietly changed the war. And there is a poetic truth in that. Progress is rarely born from perfection. Innovation is rarely born from success. History is rarely written by what immediately works. Instead, it is written by what survives lessons, by what endures through failure, by what emerges from ambition tempered with reality. So the next time you see an aircraft crossing the sky with unassuming efficiency, carrying passengers, cargo, or mission-critical supplies, remember, it did not appear from nowhere.
It owes its wings to the aircraft that could not fly, to the machines that were too advanced, too ambitious, or too early, to the prototypes that stumbled so the next generation could soar. Sometimes, the plane that no airline wanted, the bomber that could not dominate, the experiment deemed too radical, is the reason the next aircraft finally succeeds. Because in aviation, as in history, knowledge is the ultimate engine, and lessons, once learned, fly forever.